Welcome to the online causal inference seminar. Today, we are excited to have Shu Yang talk about test-based integrative analysis for heterogeneous treatment effects, combining randomized trial and real-world data. After the talk, there will be a discussion by Issa Dahabreh. We're looking forward to the talk and the discussion today. Questions today will be handled by Ying, so I'm quickly switching over to her.
Thank you, Dominic. So please submit your questions in the Q&A section. If you haven't used it before, it is just a button at the bottom of the Zoom window. And please submit your questions through the Q&A instead of the chats for us to track the questions. And we encourage you to submit your questions during the talk so that when Shu stops, pauses for questions, I would raise some of them to her. That's it. I think the stage is yours, Shu.
Great. Thank you for having me. It is my great pleasure to be here to talk about my research. And I'm really excited about this opportunity. In the past series of the talk, you may heard about different topics on combining randomized experiment and also observational studies. For example, Hido talked about how to leverage the surrogate outcomes from randomized experiment and observational studies to estimate the treatment effect on long-term outcomes that is only available from observational study. Also, Issa talked about how to leverage the representativeness of observational studies to improve the external validity of the clinical trial studies. And today I'm gonna talk about a very different objective of combining randomized trial and real-world data. Real-world data here really means observational data for heterogeneous treatment effect estimation through test-based integrative analysis. And this is a joint work with Cheng Gao from NC State, Dongling Zheng from UNC, and Xiaofei Wang from Duke. And Xiaofei is here to handle Q&A. So our research is motivated by the 21st Century Cures Act, passed in 2016. It emphasizes two things. One is big real-world data, and the other one is precision medicine. So in biomedical and health policy research, the traditional practice is the one-size-fits-all strategy. That is, patients with the same disease receive the same treatment regardless of their background. So clearly this is not effective. So the paradigm is now shifting to personalized medicine or precision medicine that aims at tailoring medical treatment to the individual characteristic of each patient. Toward that end, important step is to understand how treatment effect varies across patient characteristic, known as the heterogeneity of treatment effect, HTE for short. We know that the gold standard for treatment effect evaluation is a randomized clinical trial. This is because we have randomization of the treatment at the design stage and ensures that different treatment groups are compatible, so bias can be minimized. But RCT usually have very restrictive enrollment criteria, and therefore the underlying population may not representative of the target population well. And due to practical limitations, it may be limited in patient diversity, right? Small in sample size, follow-up is short, and the cost is very high. On the other hand, we have seen that real-world data are becoming increasingly available for research purposes. They can come from various sources, such as population-based disease registries, electronic health records, building and claims databases, and so on. And because of the real-world data collection mechanism, the underlying population is more representative of the target population. And it is rich in patient diversity, it is large in sample size, follow-up is usually very long, and the cost is low. But the key limitation in using RWD for causal analysis is due to lack of the randomization of treatment, right? Because in real-world settings, it is a patient or physician chose the treatment by their preferences or experiences. So different treatment groups may not be compatible. And we can use state-of-art causal inference method to adjust for confounding, but there is always concern about whether or not confounding has been adequately adjusted. So you can see this table really contrasts the complementary features of RCT and RWD. In fact, the 21st Century Cures Act revised the FDA's drug and device approval process by allowing the use of real-world data to accelerate the drug development. So in 2019, the agency posted a guidance for industry about how to submit document using real-world data and real-world evidence to FDA. Although there are criticisms about the real-world data, FDA believed that these data sources can and should be included if design and analysis is done appropriately. Indeed, there are successful stories in industry of using real-world data. FDA approved Pfizer's Ibrance in men with breast cancer. So this is a piece of news very recently. It's April 5th, 2019. And this approval was based on data from electronic health records and post-marketing data. We know that men with breast cancer are relatively rare. So there are fewer clinical trials that are conducted that include men with breast cancer. So there are fewer approved treatment options for men with breast cancer. And this approval was based on data from electronic health records that record the real-world use of Ibrance in men with breast cancer. So there's a clear evidence of drug efficacy. So FDA approved this label extension. This is very exciting, but in fact, this revision has sparked intense debate. Advocate says that the use of real data would streamline the development and evaluation of drugs. However, critics also argue that it will greenlight ineffective drugs entering the market. We know that in the 20th century, there were medical disasters due to anecdotal information of the treatment effect, and it has led to many deaths. So here's an interesting quote from Diana Zachman, the president of the National Center of Health Research. The irony is calling this 21st century cures when they're really talking about the standards that were left behind in the 20th century. So you can see the debate are very intense. Yet in our viewpoint, each data set actually is unique and also important in the totality of the evidence. So instead of supporting one and condemning the other, we should try to extract the information from both the data sources with greater accuracy. So data integration might be a way to reconcile the debate. There are two main approaches for data integration. The first one is meta-analysis of summary statistics, but it uses only aggregated information and it really does not distinguish the roles of RCT and RWD. The second one is meta-analysis of individual patient data. But pooling breaks the randomization of treatment from RCT, and subsequently we rely on causal inference methods to adjust for confounding. And we can never rule out the possibility of unmeasured confounding in RWD. So the goal here is to integrate the complementary features of RCT and RWD so that we can have accurate and robust estimation for HTE. Here is our motivating application. We want to evaluate the effect of adjuvant chemotherapy for early stage resected non-small cancer patients, lung cancer patients. We have an RCT data, the cancer in the leukemia group B, CALGB 9633. This is the only trial designed for early stage disease, and it included about 300 patients. So the trial was undersized to detect any clinically important improvement. Some secondary analysis showed that patients with tumor size greater than or equal to 4 centimeters may benefit from this adjuvant chemotherapy. So an important clinical question remains, who can benefit from adjuvant chemotherapy with early stage disease? And the trial alone cannot answer this question with great accuracy. On the other hand, we extracted a cohort from National Cancer Database, NCDB. This is a very large clinical oncology database that contains information of more than 70% of the diagnosed cancer patients in the US. So it is very appealing to combine both data sources for our clinical question of interest. And the goal here is to leverage the unique strength of each data source so that we can provide accurate answer to the clinical question of interest. Toward the end, here is our statistical setup. We have patient data, X, A, Y, Z, and delta. X is a vector of pre-treatment covariates that can include demographical variables, baseline health status, so on. A is the treatment, 0 for control and 1 for intervention. And Y is the outcome of interest. Z is a vector of treatment effect modifiers. And in our study, Z is the tumor size. And because we have two studies, we use delta to indicate the study participation. Delta equals 1 indicate RCT study participation. Delta equals 0 indicate RWD study participation. And then finally, V summarize all the variables. And we use the causal framework, so we use the potential outcomes framework to define the causal problem. So we imagine each subject has two potential outcomes, Y0 and Y1. The individual treatment effect is Y1 minus Y0. And the HTE can be characterized by the conditional average treatment effect given a factor of patient characteristic Z. And we make the causal consistency assumption that links the observed outcome with the potential outcomes. In the clinical world, parametric models are preferable. This is because it's easy to communicate with the clinicians. So we follow that literature. We assume that the HTE function follows some parametric model. The link function is known, but we have a vector of unknown parameters, precise 0. So precise 0 governs how treatment effect varies across patient characteristic Z. So for example, for continuous outcome, the simplest model is this linear model. And each precise 0 here quantifies how treatment effect varies across each Z. For the binary outcome, we can take the arctangent link function here so that the causal risk difference falls between -1 and 1. And we have similar interpretations about precise 0. Now we have two studies. This diagram summarizes the data structure. So we consider a superpopulation model where the target population consists of infinity number of patients, IID following some distribution. So we think this is more relevant if we want to generalize the result to a future patient population. And then on the left-hand side, we have RCT sampling. Within RCT, we have a treatment randomization. And for observed RCT sample, we have a size M, and we collect information on X, A, and Y. On the right-hand side, we have RWD sampling. Within RWD, the treatment assignment mechanism is unknown to us. And from the observed RWD sample, we have size N. Usually N is much larger than M, and we collect similar informations. Now, because HT is defined based on potential outcomes, so we require further assumptions to identify HTE. We view that RCT is the gold standard and it satisfies the following conditions throughout the talk. So the first condition says the HT is transportable from RCT to the target population. And this actually is very common in data integration literature. It has been considered by many authors. Also, this assumption holds if Z captures all the treatment effect modifiers, or if the study sample is a random sample from the target population. And in the literature, we can also have some graphical conditions to check this assumption under the structural equation models. The second one says treatment is randomized given each level of X in the RCT. And the third one says each participant in RCT has a positive probability of receiving either treatment. And these two assumptions usually hold by trial design. And because we view the RCT as a benchmark, so we will make this assumption throughout the talk. Here is a parallel assumption for RWD, although it appears very similar to the previous one, but we think the implications are very different. So we call this RWD compatibility assumption in the sense that if the RWD satisfies this assumption, then we can use the RWD to infer the HTE with great accuracy. And then we can combine RWD and RCT to estimate the HTE. In this sense, RWD is compatible to the RCT in HTE estimation. But as I said, although it appears very similar to the previous one, but the implications is very different. So here, for example, no unmeasured confounding assumption. For this assumption to hold, X must capture all the treatment confounders, right? So that this assumption can hold. This can be very strong in practice. So we view this as an idealistic assumption, which may be violated in practice. So it leads to two objectives. First, if the compatibility assumption holds, we want to combine both the data sources for optimal estimation using semiparametric efficiency theory. And secondly, if the compatibility is violated, we want to detect this violation and retain only the RCT for estimation. Toward that end, we're going to use pre-testing. So we will formulate the hypothesis, construct the test statistic, and also build the test statistic in our estimator. Oh, need to pause here to see if there are questions.
There are no offline questions, so I think we can continue. Here comes one. Is it okay for there to be a positive probability of treatment for a given covariate value in the RWD, but not in the RCT data? For example, if the covariate value violates an inclusion criteria for the RCT, but a doctor might give a patient with that value of treatment.
I think for now, we require the positivity assumptions to non-parametrically identify the HTE, but it's okay, but it's also very dangerous because we assume the HTE function to follow some parametric model. So if the positivity assumption is violated, we essentially relies on extrapolation of the information in the overlapped region to the non-overlapped region. So I think if we assume the parametric models and the transportability assumption is reliable, then we can relax the positivity assumption. But in practice, it's a dangerous practice.
Thanks.
Okay, so let me move on. Now we want to assume the idealistic assumption holds, so we can identify the HT from both RCT and RWD. So here we introduce more notations here. E delta of X is the usual propensity score. And also we have an outcome mean function and outcome variance function denoted by a mu delta of X and a sigma delta square of X. And then under the idealistic assumption, we can identify the HT by the following result. And this is a very common, popular result in the literature. It says we can have the IPW adjusted outcome, and then the mean is tau of Z, so the HT function. So one implication is that we can just take the IPW adjusted outcome and regress on Z and the delta, we get the treatment effect estimation. But this approach is very unstable if some of the propensity scores are close to 0 and 1. So we want to have some improved estimation. Toward that end, we use semiparametric efficiency theory because it provides us a principled way to construct an improved estimator. Our semiparametric model consists of two parts. The parametric part are the HT function and also any restrictions from the identification assumptions, and all other components are left unspecified. And then we can derive the semiparametric efficiency score here. It involves a key quantity here, H. H is called the mimicking potential outcome. It mimics a Y0. It is constructed in a way that a subtract from the observed outcome, the realized treatment. Therefore, it is mimicking Y0 naturally, right? And because we know that under the idealistic assumption, Y0 and A are conditionally independent given X and the delta, and this H actually inherit that property in the mean sense, in the sense that we can show that we have mean exchangeability of H and A given X and the delta. And using this result, we can easily verify that the semiparametric efficient score has mean 0. So we take the efficient score and construct the empirical version of it based on the combined data and solve for psi. And that becomes our efficient estimator. And here in the score, it involves 2 working models, one for the outcome mean function and one for the propensity score function. And we suggest using semiparametric or non-parametric methods for the 2 nuisance functions. For example, we can use methods of sieves, include a large class of basis functions, such as power series, Fourier series, splines, so on. It can provide protections against the model misspecification. And here, if you look closer, you can see that the score actually has a unique structure, right? It is a product of a residue times a residue. And it actually corresponds to the Neyman orthogonality property. And we can show that if we perturb the nuisance function a little bit, it won't affect the score a lot. So we can actually derive the root inconsistency for the efficient estimator under the idealistic assumptions. So we can impose typical conditions on the functional space to regulate the complexity. We require the 2 nuisance function estimator to be consistent, and the combined rate of convergence achieve root inconsistency. Then we can show that the efficient estimator is root inconsistent, asymptotically normal, and it can achieve the semiparametric efficiency bound. So the result here actually tells that we can pretend the efficient estimator as the solution to the estimated equation here, as if the nuisance functions are known. And we can also construct the usual sandwich formula for variance estimation, or any replication-based method for variance estimation. So we achieved our first target. So this efficient estimator is most efficient one under the semiparametric model. But I will tell you that it may be the worst. To illustrate, let's consider 4 types of estimators. We have 4 panels here. The red circle is a target, and dots are estimates from repeated sampling. So you can see if the RWD satisfies the compatibility assumptions, then the efficient estimator can hit the target very well, right? It has a low bias, it has a low variance. But the major concern lies in the possibly poor quality of RWD. In this case, our estimate will be biased, right? It actually end up here, and this is the worst case scenario. So it has high bias and low variance. So it is critical to test the RWD compatibility assumption. Toward that end, we're gonna formulate the hypothesis and construct the test statistic. For simplicity, we introduce RCT score and RWD score. That is just the semiparametric efficient score applied to the RCT data and RWD data respectively. Because RCT is a gold standard, so the RCT score has mean 0. That is ensured by trial design. And RWD compatibility may be violated in our framework. So if it holds, then the null hypothesis says the RWD score has mean 0. And then we consider 2 alternative hypotheses. The fixed alternative says the RWD score is biased with the fixed value of the bias. Under such fixed alternative, the usual statistic will go to infinity and sample size go to infinity. But in practice, especially in finite samples, there can be weak violation of this hypothesis. For example, indeed, there is no unmeasured, there is a hidden confounding, but the association of the confounder and the treatment, or the association of the confounder and the outcome is weak. In this sense, we have the weak violation. And then the fixed alternative can not capture this behavior, right? And a local alternative here is useful to study the finite sample properties under the weak violation of the assumption. And it models the bias to be eta over square root of n. Okay, so eta is usually called the local parameter. And this actually is not new. It's not invented by us. People have considered such local alternatives in other contexts. For example, the IV regression with weak instruments. And the local alternative actually compasses the null hypothesis and also the fixed alternative by taking eta to be 0 or infinity. So we're gonna study our asymptotic result under the local alternative. Now, how we're gonna construct the test statistic? We have two insights here. The first one is we take the RCT score and construct the empirical estimating equation and solve per se. That becomes the RCT estimator. And this RCT estimator is always consistent. That is ensured by the trial design. And we take the RCT score and plug this into the RWD score. If the null hypothesis is true, we expect this quantity to be small. If the alternative is true, then we expect this quantity to be large. So we use these two insights to construct a test statistic as here. So it basically measures the distance between the sample RWD score and 0, properly skewed by the variance and the covariance matrix. And we can use the standard approach to estimate the variance and the covariance matrix here. And we can show that T goes to a chi-square distribution with the degrees of freedom P, and P is a dimension of percent. And then that becomes a reference distribution. So we can take the critical values in the chi-square distribution, for example, 1 minus gamma percentile, and gamma can be viewed as a type 1 error. If gamma is small, then we know how to use this test statistic. So if a test statistic T is less than C gamma, that means there's no strong evidence of bias in RWD. So we want to combine RCT and RWD for optimal estimation. So in this case, this estimator becomes the efficient estimator, right? And on the other hand, if T is greater than or equal to C gamma, then there's strong evidence of bias in RWD. So we retain only RCT for analysis. In this case, we have the RCT estimator. Okay, so this strategy leads to the test-based integrative estimator solves this estimating equation and actually mixes two estimators, right? Depending on whether the test reject or accept the hypothesis. It chooses between RCT estimator and the efficient estimator. What will be the asymptotic distribution for the TBI estimator? In fact, the TBI estimator belongs to the class of pretesting estimator, and it is challenging to derive the asymptotic distribution for TBI estimator for two reasons. One, because the estimator depends on the random outcome of the pretesting, right? So it depends on whether the test reject or accept the hypothesis. It chooses between two estimators. And secondly, because the test and the estimator are constructed based on the same data. So the test and the estimator are dependent. Okay, so this is why it's challenging to derive the asymptotic distribution for the TBI estimator. What do you think is the asymptotic distribution of the TBI estimator? Here we have a multiple choice question. A is normal, B mixture of normals, C mixture of non-normals, and D mixture of normal and non-normal. Any guesses? So if you look at the construction here, because TBI estimator mixes two things, maybe mixture are better guesses. And because in each component, the test and the estimator are dependent. So each mixing component may be non-normal distributions. And therefore, C is a good choice. But the answer is A and D. It depends. Under the fixed alternative, because our test can reject the null hypothesis all the time in large samples, and the TBI estimator essentially becomes RCT estimator. So it will follow a normal distribution. While under the null hypothesis or the local alternative hypothesis, it actually mixes one normal distribution and one non-normal distribution. We can show that, in fact, this component follows asymptotically normal distribution, while this follows a symptomatic mixture distribution. Itself mixes a truncated normal and a normal distribution. So formally, we can show that the TBI follows a limiting mixture distribution. And here is a general result. So under the regularity conditions, we can show that the TBI estimator goes through in distribution to a mixing normal distribution. So here is the each mixing component. Here can see as a mixing probability. One is a normal and the other one is a non-normal distribution. And this is a general result, and we can discuss this in two special scenarios because in these two scenarios, the symptomatic behaviors are very different. So for example, in scenario 1, we have fixed alternative. Then the mixture distribution goes to a normal distribution. In this case, the TBI estimator has a regular behavior. While in the second scenario, where we have no hypothesis and the local alternative, then the mixture distribution actually is indexed by the local parameter eta. That means if the null hypothesis is violated a little bit around its neighbor, the distribution can jump abruptly. So this entails the non-regularity of the TBI estimator, and it causes trouble for inference, which I will talk about in a minute. And using our result, we can compare 3 estimators: the RCT estimator, TBI estimator, and also the efficient estimator. Here is a plot for the null hypothesis case. And the green one is the efficient estimator. It is unbiased and it has the smallest variance. And the RCT estimator is in blue, and also it is unbiased, but it has the largest variance. The TBI estimator is in between, right? Compared to the RCT, it improves the efficiency, but compared to the efficient estimator, it loses efficiency. But the advantage of the TBI estimator lies in the fixed alternative. In this case, you can see the efficient estimator essentially become biased, while the TBI estimator and RCT estimator still remains unbiased. The most interesting case lies in the local alternative. So you can see the RCT estimator is still unbiased. The efficient estimator becomes biased, while the TBI estimator actually is in between. It reduces bias. I haven't talked about a key tuning parameter in our TBI estimator. That is the critical value for the test, right? Actually, by varying this critical value, the TBI estimator interpolates RCT estimator and the efficient estimator. We can consider 2 extreme scenarios. In one extreme scenario, we take the critical value to be very large. In that case, we're always not rejecting the null hypothesis. So we always combine the RCT estimator of the RCT estimating equation and the RWD estimating equation for joint analysis, right? So in this case, the TBI estimator becomes the efficient estimator. And on another extreme scenario, we take the critical value to be very small. In this case, you always reject the use of RWD, and then TBI estimator becomes the RCT estimator. Right? So by varying this critical value, TBI estimator interpolate RCT estimator and efficient estimator. And the choice of the tuning parameter actually involves the bias and the variance trade-off. So this motivates us to adaptively select gamma. Okay, gamma and the critical value here are equivalent. And based on our result, we can derive the mean square error of the TBI estimator. That's a function of gamma and eta. We decompose this into 2 terms. And it's insightful to look at the 2 terms in different scenarios. So first, we consider eta to be small. So recall that eta is the local parameter. It tells how large the bias is in RWD. So if eta is small, that means the RWD has small bias. And this term is small, and the mean square error is dominated by term 1. And this term can be made small for small gamma. That is, it is more likely to accept RWD. And this makes sense, right? Because RWD has small bias, and integrating RWD will reduce the variance a lot. In the second scenario, if eta is large, and the mean square error is dominated by this term, and this term can be made small for a large gamma. That is, it is more likely to reject RWD. because RWD has bias in it, right? A large bias in it. It also matches our intuition. So based on this result, we propose adaptive selection of gamma by minimizing the mean square error with a plug-in estimator for eta. Okay, so this eta hat is a crude estimate of the bias. And in our simulation study, we actually show that this adaptive selection is very effective. Okay, so let me pause here to see if there are questions.
Thank you. I think Xiaofei did a great job in answering a lot of questions, but he also pointed out some questions that might be interesting. There is a question on, I'm not sure, semiparametric efficiency is only relevant for root n estimator. So a non-parametric HTE is not going to be like root n consistent. And yeah, and this efficiency bound conditions on correct parametric model for HTE. So
yes.
Yeah.
Yes, these are very good questions, and this is because in our setup we first consider parametric models of HTE, so we require this model to be correct. And in our previous work, we actually have a goodness of fit test for testing whether the assumptions are reasonable or not. So we can borrow that goodness of fit test in our framework too. But in this work, we mainly focus on like how, whether or when we can integrate RWD. But these are very good questions. So for a finite number of parameters, we can derive the semiparametric efficiency bound. But for non-parametric models, such bound do not exist.
Thanks. Here is another question. Rather than a binary combine versus don't combine decision, would it make sense to appropriately downweight the RWD sample? So for example, inversely proportional to comparability.
Yeah, this is a very good question. I got asked about this question a lot. So we consider 0 and 1 decision, whether or not we combine the RWD in our estimating equation here, but we can smooth this function. This is basically an indicator function, right? We can replace this by some reasonable or smooth approximation function. This is doable. I think it can improve this TBI estimator. This is kind of a hard thresholding. Softer thresholding can improve the hard thresholding estimator. But I will say it will not resolve the non-regularity of the TBI estimator. So yes, so we can replace this and it can improve a little bit, but it cannot resolve the non-regularity of the TBI estimator.
Thank you for the answer. So yeah, maybe for the sake of time, we can continue.
Okay.
Yeah. Just a quick reminder, you have around 8 to 9 minutes left.
Okay, great. I will be fast. So the last issue I will talk about is the inference, and it is difficult due to non-regularity of the TBI estimator. So the first question we may wonder, can we just use the non-parametric bootstrap? The answer is no. And this is because the TBI estimator is a non-smooth test-based estimator due to the indicator of the test. And we can formally show that the non-parametric bootstrap is inconsistent for the sampling distribution of the TBI estimator. And some possible solutions are the M out of N bootstrap or subsampling. But for those approaches, it is difficult to choose the right subsample size. So we'll propose an adaptive confidence intervals. For simplicity, we consider the kth component of precise 0, and we construct the adaptive confidence interval for the kth component here. And we distinguish two scenarios because under the two scenarios, the symptomatic behaviors of the TBI estimator is different. So the first scenario is the fixed alternative where we have a standard asymptotic. So we can use the usual confidence interval based on the normal quantiles. In the second scenario, we have a non-standard asymptotics. So we will construct least favorable confidence intervals. I will talk about this in a minute. And then the question is how we're gonna differentiate the two scenarios. So we use the test statistic T to distinguish between the first one and the second one. Because for the first scenario, we can show that T goes to infinity as the sample increases, while in the second scenario, T is a bigger OP1 term. So we can find we can also choose a sequence of values that goes to infinity as sample size go to infinity. For example, we can take kappa n to be square root of log n. So if T is greater than kappa n, then we choose the first scenario. And if T is less than or equal to kappa n, we choose the second scenario. And this approach actually has been done in the generalized moment selection in Andrew and Soares. Now, the last issue is how we're gonna construct a least favorable confidence interval under the null hypothesis and the local alternatives. We do this step by step. So for any fixed eta, we know how to construct the 1 minus alpha confidence interval because we know that TBI estimator follows a mixture distribution, right? We can just take the quantiles, the proper quantiles. And then because eta is unknown, maybe one solution is taking the infimum of the lower bound over all possible values for eta, and then taking the supremum of the upper bound over all possible values for eta. But eta can take a very wide range of values, and this solution is non-informative at all. So the solution here is we take a bounded area of eta. This area can be informed from the sampling distribution of eta hat. We construct a bounded 1 minus alpha region of eta, and then we take the infimum of the lower bound over eta in this region, and take the supremum of the upper bound over eta in this range. And here we need to take our alpha tilde to be a smaller value because essentially we ignore the tail area for eta. So this becomes the least favorable confidence interval. And in summary, we have this adaptive confidence intervals here. Depend on whether T is less than or equal to kappa n or greater than kappa n, we construct different confidence intervals. And we can show that this approach controls the type 1 error, and the equality holds under the fixed alternative. And I indeed conducted simulation studies to assess the robustness against the RWD and compatibility, and also the performance of adaptive confidence interval. I will skip the details, but the finding is that we actually create various scenarios where we have a 0, weak, or strong violation of the non-unmeasured confounding assumption in RWD. And in fact, the efficient estimator cannot control the bias well, and our TBI estimator can control the bias very well. And if the violation is small, our TBI estimator actually gains efficiency over the RCT estimator. In terms of the adaptive confidence interval, our TBI estimator here actually has a good coverage probability. Okay, and because our adaptive confidence interval has the conservativity, in some scenarios, you can see the slight wider confidence interval compared to the RCT confidence interval. But when the violation is small, we indeed see a lot of improvement in confidence interval. So lastly, let me talk about the real data analysis. So here, recall the goal is to evaluate the effect of adjuvant chemotherapy for early stage non-small cell lung cancer patients. We have RCT data and RWD data. The treatment is on observation versus adjuvant chemotherapy. And this table summarizes the number of patients by treatment in the RCT and the RWD. So you can see the total sample size in RCT is very small, whereas in RWD, we have very large sample size. We consider the following covariates: gender, age, indicator for histology, and the tumor size. And the outcome is a cancer recurrence within 3 years after surgery. And this table contrasts the covariate means by treatment group in RCT and RWD. So you can see the covariate means are actually balanced in RCT, while it is imbalanced in RWD. right? And we never rule out the possibility of unmeasured confounding in RWD. So pre-testing is helpful. Here, we formulate the HT as a linear function of the tumor size. And here's a table for RCT analysis, efficient analysis, and the TBI analysis. So we have estimator, standard error, and a confidence interval. Here is for the intercept. Here is for the coefficient associated with the tumor size. So you can see for RCT analysis, due to limited sample size, the confidence interval is very large. Well, the efficient estimator models the strength in RWD. So you can see there's a lot of improvement in standard error, but it does not test whether RWD is compatible or not. In our TBI estimator, we did this testing, and T is 1.9. So there's no strong evidence of incompatibility of the matched CDB sample. And therefore, the TBI estimator and essentially is the same as efficient estimator in point estimation, but our standard error is larger because we have a pre-testing. We take that into account. And we have a plot showing the HTE across tumor size. We have RCT, efficient, and TBI estimators. In blue, and that's the RCT analysis, we can see the confidence band is very wide, right, due to the limited sample size. And the efficient estimator here is in red. So you can see the band is very narrow, but it does not test the compatibility of the RWD. Our TBI estimator is in black. So you can see it overlap with the efficient estimator for point estimator, and it has a wider confidence band, but it is more trustworthy. It is robust. So from our analysis, if the patients with tumor size in this range, you can see we have significant results. So patients with tumor size in this range can significantly benefit from adjuvant chemotherapy. In summary, we have a test-based approach that integrates small data with high quality and big data with possibly poor quality for accurate and robust estimation of HTE. We have adaptive combining procedure. We have adaptive inference procedure. And in our future work, we may extend this framework to sensor survival outcomes. This is because survival outcomes are most common in cancer clinical trials. And we also need to develop methods to handle other issues in RWD, for example, measurement errors, missingness, data structure misalignment, so on. So there are a lot of opportunities along this line of research. Lastly, I thank my collaborator in the funding agency. Thank you for your attention.
All right, thank you so much for a very nice talk. I think in the interest of time, we should move directly to the discussion, then we can take questions after the talk. Yeah, Issa, whenever you're ready.
Yeah, let me see if I can repeat the trick of sharing my screen. Okay. Seems to be working. Can people see it full screen?
Looks
yes.
Good, yeah.
Okay, I've gotten better at this. So thank you to the organizers for having me. And thank you very much, Shu, for sharing your work and the paper way ahead of time and walking us through your results so carefully. So here's the main idea of my discussion. Taking the causal assumptions as given, I think this is an impressive piece of technical work. I learned a lot working through it. And again, Shu was very kind in sharing way ahead of time. Now, the unfortunate thing is, despite my dual appointment, I have the mind of an epidemiologist, the heart maybe of a statistician, but the mind of an epidemiologist. And for anyone who knows, that's like the wrong way. You want the mind of the statistician and the heart of the epidemiologist, but we get what we get. And so, since I'm an epidemiologist and actually almost, you know, that I came that close to being a real doctor, most of my discussion is going to be about what this means, what are the assumptions, what are the concepts. I'll make some points about the estimation aspects, but I view those as mostly minor quibbles in the bigger picture. Okay. And so throughout, I'll retain the focus on point treatments and outcomes measured at the end of the study, even though, as Shu says very clearly, this is perhaps not the most interesting case or the most common. Usually we have failure time, outcomes, and sustained treatments. But even in that case, in the very simple case of a point treatment and an outcome measured at the end, I think there is substantial causal and semantic questions I'd like to ask. And let me be completely honest, I'm asking those for my benefit. So if Shu has answers or if the audience has ideas, I plan on adopting them because I am stamped by some of these issues in my own work. Okay, so here's my first question. I don't really know what is capital italic A in this paper. Here's what I mean. It's called treatment in the paper and in the presentation. But is it the assignment indicator in the trial, or is it the received treatment indicator in the observational study? And I claim this is a non-obvious problem. In the trial, you can conceive of situations where what is assigned and what is received for a point treatment are both well-defined, and they don't have to be the same. There can be non-adherence. I'm going to return to non-adherence near the end. So people can take the first treatment, the other treatment, they can take nothing, they can take something that's not in the treatment. And so one needs to pick, am I using the assignment indicator or the observed treatment? Now in the observational data, the situation seems to me to be worse. Typically, it's unavailable. We know what people took, but we don't know what was recommended to them in most cases. And as my colleagues, to whom I give credit here, have impressed on me, actually, the idea of a recommendation may be ill-defined. For example, if the patients can do whatever they want without listening to a doctor, just go to a pharmacy and pick up a medication, then there's no sense of a recommendation being made. And again, it would never be captured. And so it seems to me this is a non-trivial semantic difficulty. And then I'll return to non-adherence in a second. Now, I'm not asking this to be difficult because I have data like Shu's from other applications. And I really don't know what to do in my data. If I only have the assignment indicator and the received treatment indicator, which I believe may be the case in the NCDB example, then how do I line them up? And if the idea is to use the received treatment, both in the trial and in the observational study, then assumption 2, which is the no confounding in trial, seems to me to be on par with assumption 3, because there may be unmeasured causes of the non-adherence in the trial. And so if the two assumptions are on par, I don't see any logical reason to pick one as more plausible as the other. And so the parameterization seems to favor violations of assumption 3 versus 2. So that's the first kind of question. What is A? How do I think about it? Now, assumption 1, it does a lot of hard work in the paper. I claim it has two parts. The first part says conditional on the high dimensional X, the mean of the individual treatment effect is independent of the data set. And that is fine, I think. If one has a very big X, that's fine. And then there is part B, which says the mean of the individual treatment effect given X in each of the data sources equals the mean of the treatment effect conditional on the much lower dimensional Z. In particular, in the example, Z has one variable, right? Tumor size. And so this is, okay, I'm being a little obnoxious in this one comment. I hope Shu can tolerate me. I have invoked assumption 1 several times. And the only reason I'm being obnoxious and mentioning this is, please don't say that, you know, the epidemiologists assume the means are exchangeable, because it's a basic epidemiologic idea that maybe you only have exchangeability of the conditional average treatment effect over delta. And so this assumption, I'm willing to go with it. Part B, though, seems to me a little less plausible. Okay, informally, I think part B says the individual treatment effect is mean independent of the part of X that's not in Z and the data source indicator, the delta, given the Z. And so when Z is low dimensional, I saw the audience has a similar concern to mine, like why not model it non-parametrically? That's fine for estimation. It's, I think, an interesting question. But more to the point of the assumptions, the individual level effect of chemo, no one believes is mean independent of all covariates and trial participation given tumor size. It would be very strange, I think, to have the part B. Okay, now, my third question is it really, really true that there are no restrictions from the identifiability assumptions on the observed data? And so I understand that throughout the paper, there's no assumption that there is common support between delta 1 and delta 0. But in practice, the density of the high dimensional X will have at least some sliver of common support between the trial and the observational study. At least that's been my experience. And so, for example, in the chemo problem, I think most people would believe that the healthiest people in the observational study can have overlap in their covariates with the sickest people in the trial. And so some overlap, I think, is not unreasonable. And so then if I combine assumptions 1 through 3, for every X value in that sliver of common support, and I realize you don't want to assume it's big, but I feel like it's almost there. This one seems testable. And so the immediate question is, should there be belief and evidence in the data that there is common support? Could someone just test this and avoid, reject? This will almost always reject in large data sets and maybe stop there, or is there a reason to go through the score based test? Now, in claiming that the methods have no observed data implications, I feel there's also a practical risk that we will ignore that there is common support in any reasonable application, giving rise to this problem. Okay, now, I'll be honest, a question on 4 and 5, I put some graphs in, but there is not enough time to discuss the graphs. I have my discussion of the graphical arguments at the end if people are really interested. My reason for including the graphs without much discussion is that one of the organizers has issued, I believe, a public challenge on whether graphs can be useful for causal inference. And so I volunteer to offer a case example where graphs make a huge difference. Okay, now, here I just want to go back to non-adherence. And so remember that I feel like we need to think about recommendation versus receipt not being the same. And so the people I work with typically believe that trial participants are more likely to be adherent than non-participants. And in some cases, the difference is striking. So for example, in screening, lung cancer screening interventions, sometimes the adherence in the trial is 90%, 95%. And then when you try to apply the same screening outside of the trial, you get 50% adherence. So massive differences. And so this is just to say that when that happens, there is the possibility of common causes of participation and adherence. And when you get those common causes, I feel like assumption 1 becomes a very unusual coincidence. In particular, in this graph, the mean version, or the distributional version, I should say, the distributional version of assumption 1 doesn't hold, and the mean version seems, and the mean difference version, which Shu uses, seem to be kind of unusual coincidences. Related to the point of non-adherence is not only that participation and adherence have common causes, but that participation will often have a direct effect on adherence. So basically, I call the people up because they're in my trial. I remind them about my trial. I tell them, could you please do what you're supposed to be doing that we assigned to you in a randomized way. And this creates the possibility of engagement effects through adherence. I don't have the time to do the graphical arguments for that, but the big picture point is that the participation is not easy to separate from the recommendation because of the effects of participation on the outcome through adherence. And of course, direct effects on the outcome are also possible, but I didn't put them here to keep this a little simpler. Now, I should say here, I'm painfully aware that these two questions apply to my own work. I have a crisis of faith in a lot of the transportability stuff. And so please, this is not nothing is a criticism here. It's more like things I worry about when we do this. I do think, though, that the questions are accentuated when we combine data sets with very different designs. Okay. Question number 6 is, it's a holy grail to use the data to decide if they are compatible. And so I think this is very valuable work here. And the adaptiveness of the procedure, I really like thinking about that. My question is, given that the dependence of the procedure on a very long chain of assumptions, can we reasonably rely on it to determine combining or the weights by which we combine? Meaning, if the procedure, as I think is framed in the paper, addresses the implausibility of assumption 3, which is no confounding in the observational study, don't we need to be absolutely certain about the others? And if we do, I feel like assumption 1 is at least as problematic as assumption 3. Not problematic in a math sense. Logically or in practice, I can't see how I would pick to promote one as more plausible than the other. And then, especially if you consider the semantic difficulties with treatment and adherence and all that. So question 7, and I really hope Shu will say no and have a resounding, convincing answer. But I feel like we are a little far from plausible assumptions for practice. And I'll quote here Sander Greenland because I cannot match his flair or style or convincing argumentation. But basically he says, in a complex problem like this, with non-adherence, with possible trial engagement effects, with selection of participants to be more adherent, semantic vagueness about the treatment and all that, there is a difficulty in formalizing a complex, however essential task, especially since the motivation of the work seems to be to convince regulators to promote the use of this, say, in the decision of the FDA. One might say that this is a very difficult task, very high bar. And so might we just as well be informal or a little more informal, at least whenever we believe that we are far from identification under realistic assumptions. Let me hasten to say here that I don't mean informal, like just squinting at the data or doing the naive things, but perhaps the base case is a separate analysis of the two data sets that acknowledges the difficulties of each one and compares. I have one more slide.
Okay, great.
Don't let the counter fool you. Yes. So this is it. I really wanted to thank Shu again for the wonderful work and sharing it and the presentation. And this is just a list of the questions I went through in case it helps with the discussion. Thank you very much.
All right, thanks for a nice discussion. Shu, do you want to quickly respond?
Yeah, I think that in the end, I mentioned that there are a lot of troubles in RWD, for example, missingness and measurement error, so on and so forth. But again, there's also a lot of trouble in clinical trial studies, right? So just to mention that, bring up a lot of the issues in trial analysis. So in our framework, we view like some clinical trials are well designed and some clinical trials may be poorly designed, including a lot of non-compliance issues. So this turns the clinical trials into observational studies, right? And we rely on causal assumptions to tease out the treatment effect. So I think these questions are great. That opens a lot of problems, and I think this is a very interesting topic and a very interesting line for future research questions. So I don't think I can have a lot of time. I think I can discuss with you offline.
Can you just say what's A in the setup?
We have observation that is no chemotherapy, and the other one is receiving the adjuvant chemotherapy. So these treatments are well defined in in practice. So in this case, like people know whether patient received the treatment or
but
not.
I mean, in the observational study, it's what they actually got, right? That's how the NCDB works. In
Yes.
the trial, do you use what they actually got?
Yes.
Or what they were assigned to?
They will be administered. So people, the doctors know which treatment they received.
And so assumption 2 is on par with assumption 3, correct? They both can be very wrong.
Yes.
All right. Thank you all. I think we should now wrap up and maybe we can take some of the discussion after that. First, thank you, Shu, for a very nice talk, and Issa for a very interesting discussion. Also, thank you to Xiaofei for helping out in Q&A today. Next week, we're going to have a talk by Tyler Vandervelde from Harvard University, who will talk about causal inference and measure construction towards a new model of measurement. We're all looking forward to that. I hope you all have a great week. Thank you all for coming, and see you next time.